we'll get started here. So what you want to do is you want to review through your notes. If it's, a good thing to do is if it's some of the memorization is difficult, you should review them every day. If you read through them every day, it's a lot easier to memorize. It's just a repetition. It's like advertising. Sometimes you forget about something, and that's why you're bombarded by advertisements, because it's just to keep it in your memory. All right. And so you'll want to do that, but not only just read through it, just make sure you know the information, but also to practice the problems, because you should be able to do and understand all the problems that we do in class. And sometimes people look at the examples and not really break those down. And then it's often a trap where you think you understand it, but when you actually sit down to do it, it's a different story. So just make sure that you go back through the problems and try them without looking at the solution. And so what did we cover then so far? Yesterday, what was it? Gases? Was that it? Just gases? Did we do anything else? Dimensional analysis. Dimensional analysis and gases. Then what about the things about, algebra and multiple unknowns and dimensional analysis? Was that clear, or being clear, you should be able to explain it to other people. How do you know when? Well, how you know is you try it and then you see if it works. I mean, for example, that temperature, the delta T, we could have tried it and we could have gotten the number, like if we just plugged it into degrees Fahrenheit is equal to 9/5 degrees C plus 32. If we plug it in there into the algebraic equation, and then we see a temperature drop of 50 degrees Fahrenheit, it's 47. There's something not quite right about that if you know the numbers. And so, knowing something, a little bit about the numbers as a reference point can save you from the wrong answer, because sometimes you don't know which equation or which approach to use, so you just try it and see. Normally when you're coming up with a two equation, two unknown, is because you tried everything else and nothing else seems to work. You aren't making any progress. And so those are the three that you'll encounter in chemistry. Yeah. All right, tomorrow we're doing Charles' Law. Charles' Law deals with the gases chapter. So we haven't quite gotten to Charles' Law. We're getting to Charles' Law today. But what you want to do is you want to skim through the experiment, read the objectives and the discussion, and just get just kind of a general idea. This is 1787, it's a long time ago, that Charles made the observations. And so Charles was interested in pressure and volume. Pressure and volume of gases, and the relationship between pressure and volume. So we took observations on pressure and volume. So the first thing is, how do we measure pressure? And so we have mechanical pressure gauges. We could put a pressure gauge on the container. Dial gauges. That's one way. These dial gauges, there are different types of dial gauges. Some dial gauges have a diaphragm inside there, and the gas pushes on that. Others have a spring. Others use different ones. I used to use a fancy pressure gauge for vacuums. This fancy pressure gauge measures the thermal conductivity. Have you ever used a vacuum thermos? A vacuum thermoses are really nice because they'll keep your hot beverages hot for a long time and your cold beverages cold for a long time. But vacuum thermoses are kind of expensive because of the construction. What they have is they have a double-walled construction. I don't know if I want to go off on this side here.
The other option is an insulated mug or an insulated thermos. An insulated one is different than a vacuum one. As chemists, we like the vacuum. We call them vacuum dewars or vacuum containers. And so if we look at this here,
it's a double wall construction, and so normally, around the inner wall you'd have insulation, like a home insulation or something, some styrofoam or something to insulate it. Right? But if you have insulation here, there's going to be heat transport through the insulation through the air in here. But if you have a vacuum, what you want is empty space there, because if you have something that's vibrating madly, like the inner wall of the thermos, because of the kinetic energy, right? It has to translate that kinetic energy to the outer wall. But if there's empty space, there's like nothing in between the inner wall and the outer wall, then we have no transfer of kinetic energy, because like you touch a hot object, all that motion gets transferred to your skin, and your skin cells or atoms or molecules are going to start vibrating at high kinetic energy. And so here, if you have nothing here, there's nothing to transfer the kinetic energy, and therefore there's no heat transfer. If this were a perfect vacuum, then you'd never lose any temperature. If this were a perfect vacuum, if it were a perfect vacuum, you'd have like 5-inch thick steel walls here and other containers. It's not going to be a perfect vacuum, but as long as they can reduce the amount of gas, then you're going to have less thermal transport, and it should stay warmer longer. And so the very fancy gauges I use had a hot probe and a cold probe, and it just measured how much heat was transferred between the hot probe and the cold probe, and then from that you can get a gauge of how many particles are in the gas and determine the gas pressure by calibration. Let's see. Let's continue on here.
we talked about this, right? Okay, so we're talking about measuring the pressure of a gas here.
When we think about the pressure, it's the force. The force of what? What's pushing against the inside of that? You're going to feel the gas pushing. Actually, I'll demonstrate this tomorrow. But you'll feel. It's like when you go underwater. If you go deep underwater, do you feel that water pressure pushing on you? Well, the same thing here. You don't notice it because we're accustomed to it. But it's the force of the particles colliding. It's the force of the collisions is what it is. And it's the force of the collisions of the gas particles colliding with the surface. That's what we're talking about before. So the more collisions, the higher the pressure. The more collisions, the more gas we have. Or the higher the energy of the collisions, that is, the higher the temperature, the higher the pressure. And so the force is going to depend on how concentrated the gas is, and what temperature the gas is. How concentrated is volume? Small volume, it's crowded. Big volume, it's less crowded. The amount of gas, of course, and temperature. These things are affected pressure. This slide's not important. I wouldn't even bother writing about it, except this: pressure equals force over area. We're going to talk about these factors later. Another way of thinking about pressure is the weight. When you swim underwater, you feel the weight of the water on you. And the deeper you swim, the heavier it is. Like 1 gallon of water weighs how much?
8 points. something pounds.
Yeah, 8 point something pounds, 8.3, 8 1/3 pounds roughly. 1 gallon of water weighs 8 1/3 pounds. That's a lot, right? And so if you're swimming underwater, it's going to be feeling very heavy. Well, air weighs a lot less. Air is about, how much less would air weigh about? If water weighs about 8 pounds per gallon, then water would weigh about 8 pounds per. This is very rough because it'd be more. How do I know? Because I know the density of water is 1 gram per milliliter. The density of air is about. See, these reference points, how do you know? Well, you either just don't bother because it's just obscure information, or if you've seen it every day, by the time the final comes around, if it's in your notes and you read your notes every day, how many times have you going to seen it by the time the final comes? If you see something 50 times over and over again, okay, what's the price of something that that you see all the time? Gasoline, maybe? I'm sure you can come up with it. If somebody tried to sell you gasoline at $10 a gallon, and they said that's the fair price for gasoline, what would you say? You'd say, no, thank you, right? The same thing. People come up with these numbers when they do the calculation, and it's like somebody trying to sell you gasoline at $20,000 a gallon. And what do? You say, that's a ridiculous number. It's a ridiculous, I made a mistake in my calculation. But they should have caught that mistake, right? But a lot of people don't catch that mistake. They'll just go ahead and say, this is right, this is the correct number, $20,000 a gallon. That's what I punched out, And so you need some numbers for reference. That way you don't come up with ridiculous numbers, and then when people talk numbers, you know what they're talking about. In science, people talk numbers all the time. I went to a conference once, and there was this guy, Henry Weinberg, who's very, very famous chemical engineer from Caltech. And he moved to UCSB. I was there. Actually, he moved, I think, right before I got there. But he's one of the, he's considered like the father of ultra-high vacuum, basically. And he was at a talk, and one person came up with a ridiculous number during the talk, and so he just asked him about it, but the presenter didn't have a grasp of the number. The number was completely ridiculous. It's like saying $20,000 per gallon for gasoline or something like that. And so he just called, and it was very awkward because the presenter had no idea what he was talking about. Okay. He didn't realize he was wrong.
The answer is 0.0012 grams per liter.
Yeah, or 1.2 or 1.3. Our slide had 1.3. Our PowerPoint had 1.3 grams per liter. And the density. Do you guys remember the density slide?
Oh, yeah.
Is that the one?
That was it.
Oh, that was it? 1.2? All right. Where did I see 1.3? All right, 1.2. So it's close, but it's about 1,000 times off. So if water weighs 8 pounds per gallon, then air would weigh about 8 pounds per 1,000 gallons. And so you get 8 pounds per 1,000 gallons. Actually more, because it's 20% more, right? And so it'd be more like 10 pounds per 1,000. So these are little numbers, because people talk numbers in science. You talk numbers too, and so when you talk numbers like this. You try to figure things out. It's not just straight memorization. It's being able to manipulate numbers. Well, how do you do that? Well, you have to have some numbers memorized. Well, 8 pounds per 1,000 gallons. That's still a lot, because how many thousands of gallons of air are sitting above us? We're deep. We're very deep. Because how far does the air extend up in altitude?
Very high.
Really high. Really high. And so that means there's a lot of air above it. If we were swimming in water, we'd be completely crushed at this, depth. But since we're swimming in air, we aren't completely crushed. And we would be crushed if we didn't have internal structure. You know, we would be crushed. Like, for example, if there was empty space inside of us, how thick of stainless steel walls would we need to protect ourselves from imploding? Like 5-inch thick stainless steel. Why? Because we got 8 pounds per 1,000 gallons, and we've got so much air above us. You know, we're literally swimming under an ocean of air. And so swimming under this ocean of air is 15 pounds per square inch of pressure. And so that's how much of the air weighs. The air weighs 15 pounds per square inch. And so when we're thinking about this, here, we can come up with a balance. And so at sea level, it's around 15 pounds per square inch here. Pounds per square inch we could call PSI, to abbreviate PSI, 15 pounds. This is what we call the atmospheric pressure.
Isn't there 1 atmospheric pressure for every 30 feet of water or something like that?
Yeah, right. So if you go, well, we could figure it out, actually. That's a pretty interesting thing to do. We could figure it out. About 30 feet. About 30 feet. Actually, we'll figure it out right now. So we have 15 psi, pounds per square inch. But what we want to do is we want to put a weight there on the other side. Okay, what can we put as a weight on the other side? On the other side, you know, I could put some steel weights, right? Now, this is a balance here. I can put some steel weights. I could put, well, steel costs money. Water is cheap, right? I could put water. How much water will I have to put on the other side to equal this? So, if I wanted to do the same thing, okay, let's take a square inch here. How much water would I have to put to equal 15 pounds of water? Well, that sounds like almost 2 gallons worth of water, right? And if I did that in a square inch, that 2 gallons would extend up to 30 feet, roughly. Actually, I should do a more precise calculation. I'm going to do a more precise calculation, or more accurate calculation. But, you know, 30 feet of water is too much. And so I'm going to use a liquid to put on the other side. I'm going to put it in a container. It's going to have 1 square inch, let's say. And I'm going to use the most dense liquid I can think of. What is the most dense liquid you can think of? It turns out it's mercury. Mercury has a very high density. Do you know what the density of mercury is? 13.6. Is that more dense than lead or less dense than lead?
More than that.
Then this is more dense than lead. Have you ever picked up a lead brick? You can. I'll bring a lead brick in. Let's pick it up. So if we use liquid mercury as the opposite weight, then we're going to have a column of liquid mercury almost a meter high, 3/4 of a meter. In fact, it's going to be 760 millimeters tall. And then if I had a column of mercury 760 millimeters tall, that would weigh the same amount as the atmosphere weighs here at 15 psi. I have how many thousands of feet of atmosphere? You know, so this many thousands and thousands of feet of atmosphere is equivalent to just 760 millimeters of mercury. Mercury is so dense that, you know, you could take copper balls. I think it's shown in one of those. And will copper float on mercury? Would lead balls float on mercury?
Yes.
Yeah, lead balls won't sink. Lead balls are going to float. How about gold balls?
Yes.
No.
Gold balls would sink because gold is around what?
19.9.
Yeah, around 20. So, we're good. And so mercury is usually chosen because it's it's very dense, and we need a liquid because of the design, because it's not just simply placing. If we're just placing it on one side, we would have a solid. It would be a lot easier, like the triple beam balances we used in the laboratory. And so the construction of this is this. This is the balance. On one side, you have the weight of the atmosphere pushing down. On the inside of this, you have the weight of the mercury pushing down here. And inside here, we have a vacuum, so there's no gas in there. And so the two weights are going to be equal here. This is the weight of the liquid mercury. This is the weight of the atmosphere. And it's a balance. Now, what happens if the atmosphere starts to weigh more? If the atmosphere starts to weigh more, then the balance is tilted like this, right? And what's that going to do? It's going to push up this side higher. If the atmosphere weighs less, then the balance shifts the other direction, and this side goes lower. And so what we're going to do is this. We can figure out, well, that's 15 pounds of mercury. This is 15 pounds of mercury per square inch, right? But, you know, we don't want to hassle with calculating how much that mercury weighs. What's much easier is this. You know, if it goes lower, then it weighs less. If it goes higher, then it weighs more. And so instead of doing the weight or the pounds or the force, what we're going to do is we're just going to do it based on the height. You know, the higher it is, the higher the pressure. The lower it is, the lower the pressure. And so even though millimeters of mercury is a length, this is millimeters of liquid mercury, this is a length. Equals a length or height. And this is just proportional to the weight, which is proportional to the pressure. And so we're just going to say this is proportional to the pressure. It's not exactly equal to the pressure, because how can you say, you know, 760 is 15? Well, somebody already figured it out. That's it. And so this is how a barometer works. A barometer works like this. Okay, so what we have is normal atmospheric pressure. Normal atmospheric pressure is 760. However, if some hurricane blows through, then the atmospheric pressure goes down, right? And so this is what I was talking about the other day. If a hurricane blew through here, we'd worry about the windows. So people board up the windows and do that kind of stuff. Because if the pressure inside here is 15 pounds and the pressure outside is a lot less, then there's an imbalance in pressure, and it could have a pressure explosion like a balloon, you know, popping. Kind of thing. So when we characterize gases, we like to know what is the pressure of the gas. The higher the pressure, the more gas you typically have in there. Like say, if you were to go buy some gas, would you just buy it based on volume? So, you know, I have a good deal on helium gas. I'll sell it to you for, you know, $1 a liter. And then somebody else says, no, I'll sell it to you for 50 cents a liter, right? Are you going to get the same amount of gas? Maybe, maybe not, because we need to know not just the volume, but we also need to know what the pressure is, because somebody could sell you an empty tank of helium gas. Yes, it has helium still in there, but it's empty because that helium isn't coming out unless you have a vacuum, right? It's stuck in there. Or a full tank. A full tank of helium weighs a lot more than an empty tank, you know, but the volume's the same because it's fixed by the tank. And so we need to know the volume, we need to know the pressure. And if we know the volume and the pressure and the temperature, because the temperature is going to play a role, then we'll know the amount, you know, how much gas is in there. The amount, you know, that's fixed. If you have 20 grams, we usually buy gas by the grams. And so we'll buy like 2,400 gram tank. That means we have 2,400 grams of helium in there. It doesn't matter what the pressure is, it doesn't matter what the volume is, temperature. You know, if I change the temperature, is that going to change how many grams I have? No. The same thing with the volume and the pressure. Uh-huh. Oh, question?
Why is it that when you fill, like let's say I fill my car tires with
Uh-huh.
air, why is it that if you had the tire off the car and you tested it, it would be like 32 psi, and you put it on the car and tested it, the pressure wouldn't change even though you've had it the whole weight of the car to the tire? Why does that have a difference?
Okay, did you measure the pressure right after putting the tire on?
Yeah, I mean, like you can fill tires and put them on the car. Like if you want to get exact measurements, whatever you fill the tires.
Yeah. Okay, if the tires were like solid, rigid, that the volume didn't change, then pressure should be the same. But what's going to happen is the tire is going to deform a little bit, and so that could cause pressure to change. But there could be other factors as well. But you have to think. Otherwise, if the volume is the same, the temperature is the same, and the amount didn't change, then the pressure should be exactly the same. So it has to impact one of these particular, volume. However, when you drive the car, the pressure does change because they have cold pressure and hot pressure. So when you normally inflate the tires, they're supposed to be cold.
So weight doesn't play a part of it.
Weight is going to play a part of it, but the weight of the car is going to deform the tire, which changes the volume. The weight, the tire should not be, if the tire were made out of solid, like the solid structural material, that wouldn't make any, actually that wouldn't deform under the weight of the car, then it's not going to change. Yeah, at all. Not change. Well, anyway, let's go back to pressure. And so 760 millimeters of mercury is just the average weight of the atmosphere at sea level. You get the equator. But, it changes. So the weather reports always report this, except they use USCS units rather than metric units. They use inches of mercury. And even this is not the metric unit of pressure. Metric unit of pressure is something else we'll talk about. But we usually hear it in inches of mercury. Well, how many inches is that? Inches of mercury. Let's take a look. So what is normal pressure? Well, what is the, how would we do this conversion? So if I want to go 760 millimeters of mercury equals how many inches of mercury? How would I do that? Dimensional analysis. And so what we do is we take 760 millimeters of HG liquid, and then we look for conversion factor. Is there a conversion factor that gets rid of millimeters of mercury? Do you know conversion factor for millimeters of mercury? Not yet. We will have it. How about a conversion factor for millimeters? Yeah. Well, give me a conversion factor for millimeters. They're going to be 1,000 milliliters per meter. And so we'll just do a millimeter to meter conversion. And then we're going to go from meters to, where should we go next? Meters to, do you know the number? No. So let's go meters to something else.
Where are we trying to end up?
Inches.
Inches. Okay, inches.
Well, let's go to meters to something else. Yeah, meters to centimeters, sounds good. 100 centimeters per meter. And then we need to get rid of centimeters next. Where can we go from centimeters? Yeah, 2.54 centimeters per inch. So how many inches is that? And so this is just your average pressure. So it's by 1,000 times 100 divided by 2.54. It's 29.92. 29.92. Just go with inches. So the normal pressure, this is what we call normal atmospheric pressure, or normal barometric pressure, is 29.92 inches. That's mercury. Well, how much does mercury weigh? Weighs a lot. It has a very high density, right? So, about 15 pounds of mercury. Well, what would the equivalent in water be? Well, water has a density that's 13.6 times. Is it 13.6? Let's look at the density. Density of water, 1.0 grams per milliliter. Density of mercury, 13.3. 13.3.
I thought it was 19.
Oh, it's gold.
Oh, that's gold.
Yeah, liquid mercury. 13.6. 13.6.
Yeah.
So what this means is this. If I have, let's say I have 15 pounds of mercury. If I want 15 pounds of water, then I'm going to need how much more volume? Am I going to need more water or less water to equal 15 pounds? More water. How much more? I'm going to need 13.6 times more water. And so if this is the height in mercury, liquid mercury, then I could just do this as an additional. And so I have 29.921 inches of mercury. And so what I'm going to do is I'm going to go from inches of mercury to inches of water. And so what we could do is we could say this: for every 1 inch of liquid mercury, we would require 13.6 times more inches in water to equal the same weight because of the difference in the densities. So this will be 13.6 inches of water. So let's go ahead and do that. .9 inches. 406.9 inches of water compared to 29.921. And so this is the reason why they don't use water. Water is a heck of a lot cheaper. But you know, if you're going to make a barometer using water, and this is why it's a liquid here, because we can have this surface here. And so if we made this out of water, how tall would we have to make this tube? It'd have to be at least 400 inches. It'd have to be higher than 400 inches. Well, how high is 400 inches? Well, let's convert that into feet. How many feet is that? So this divided by 12 inches per foot is 33.91 feet. 33.91 feet. So we'd need like a 3 or 4 story building to house this, or we'd have to put it outside, but then we'd have to worry about airplanes and that kind of stuff, right? Birds hitting it. And so this would require a 4 story building to build this. Whereas barometer, we have a barometer in the lab. The barometer in the lab is just 1 meter tall, roughly. And so we don't. And so this will tell us, you know, how much does the water weigh? If you go swimming in the ocean, let me tell you. If you go swimming in the ocean, what is the weight of the air here? The weight of the air we call 1 atmosphere, which is 760 millimeters of mercury, which is about 15. It's not about, let's give you more precise. It's 14 point, actually, what does the book say? The pressure.
Pressure.
Actually, I have it here. 14.70 psi, or 14.70 pounds per square inch. Okay, this is air. And so I got about 14.7 pounds of air here. And then if I go 33.3 feet deep, let's go about 34 feet deep. If I go 34 feet deep underwater, then I would be at another atmosphere, but I'd be at 1 atmosphere of water. This is 1 atmosphere of air. And so this would be 14.7 pounds of water, liquid water. And so, in other words, if I'm swimming here, what is the pressure? Total pressure. The total pressure is going to be what we call 2 atmospheres, or about 30 pounds. 30 pounds. That would be pretty crushing, actually. Even if you go like 9 feet deep, 9 or 10 feet would be a third, so you're about 1.3 atmospheres. Does that make sense? So we're looking at the weight of these things on top of us here. I didn't have to do the calculation, it was here. But I talked about metric units. Actually, in the international community, they use SI units. The SI units for pressure is the bar. The bar has a physics definition. The bar is not the weight of the atmosphere. The bar is the force of like 1 kilogram, et cetera, et cetera. So it's more of a physics definition. But it turns out a bar and an atmosphere are close. You know? And so we'll talk about that in just a minute.
Before we continue, I have a question. So it's 34 feet of H2O for 1 atmosphere.
Yeah.
But since it's seawater, there's
Seawater is more dense, and so you won't have to go as deep. Seawater has a density of about 1 point. What was the seawater density? Well, it depends on where you're swimming.
1.02.
Yeah, well, there are places where it's a lot more dense than that, actually, and there's places where it's less dense. So let's just look at the average density of seawater. And so that will change it a little bit. They do it by parts per trillion here, as far as the salinity goes. Here it is, at the surface, 1.025. Kilograms per liter is the same as a gram per milliliter. And so about 1.03. So it's not that different. It's just 3% different. When you look at the salinity here in their diagram, it's in parts per trillion. Mediterranean Sea is at 38 parts per trillion. Red Sea is at 40 parts per trillion, but the average seawater is 34.7 parts per trillion. All right. We'll talk more about the units here. But what we're going to do is we're just going to come up with a table where we just list all the units and their equivalencies. And so the bar is just sitting out here alone. And so let's do this right now. Ignore that bar there. What was 1 atmosphere again? Yeah, but what does it refer to? 1 atmosphere refers to what? Yeah, it's just your average pressure at sea level. If you go up in elevation, the pressure becomes less. But 1 atmosphere, and then that's equivalent to 760 millimeters of mercury. But in this case, it's defined. So we might as well pick a reference point, and this is the reference point. So this is defined as the weight of 760 millimeters of liquid mercury. Which is equal to 29.92 inches of liquid mercury, which is equal to 33.91 feet of liquid water. 33.91 feet of liquid water. That would weigh the same. Which is equal to 14.70 pounds per square inch. Which is not equal to 1 bar. So what is 1 bar equal to? So, what is a Pascal equal to? So this is what a Pascal is equal to. Pascal is equal to, well, 1 atmosphere is 101,325 pascals. Pascal, this comes from physics. So we aren't going to worry about it. Have you ever heard of a Newton?
I think 14 points is like 15 PSI does equal 1 bar. Isn't that the equation?
Close, very close, but not exactly. Which is equal to 1.01325 bar. And so in SI units, SI uses the bar instead of the atmosphere. But when you look at the atmosphere and the bar, they're so close to each other. 1 bar, 1 atmosphere, almost the same thing. And instead of saying millimeters of mercury, they say millibar, which this would be equal to 1,013.25 millibar. And so a millibar would be increments like a millimeter of mercury. And then we have the bar, which would be like the atmosphere here. And so oftentimes when you hear pressure reports, they don't say inches of mercury, they say millibar. How many millibar is it today? Or how many bar is it today? Depends if you want to say. The barometer, what can you say about the barometer? The barometer is made to measure room pressure. The barometer is made to measure atmospheric pressure. The barometer is made to measure, the pressure of a gas outside. But we have another thing. It's called the manometer. The manometer is made to measure the pressure of a gas sample. So. Gauge pressure and absolute pressure, let me talk about that later. But we use mercury for the manometer too. And the way we do it is we think of it as a balance. And I like to do it differently than the book. Here we have a balance, so we set this level here. And so the left side weighs the same as the right side. The left side weighs the same as the right side if the balance is level like this. If it's not level, if it's like this, then the left side and the right side don't equal each other. That's the equal pressure level. The same thing here. Now, what we do is we find the lower level. And so the left side is equal to the right side here. So wherever the lower, if we pick the upper level, then we're slicing the gas in half here. Or not in half, but slicing part of it off. I don't like these equations here. I don't like those equations. I like to write it differently. In other words, I like to think of the weight of the left is equal to the weight of the right, regardless. And so let's say I have a gas sample in here. I want to know how much this gas weighs, That is, what is its pressure? And so on the first one, I'll have, this is called a manometer here, this U-tube. All it is a U-tube filled with mercury. Now mercury hates glass. Water loves glass. So water creeps up the sides, but mercury curls up and tries to avoid contacting glass. And so what mercury has is it has what we call a convex meniscus, whereas water has a concave meniscus. You know, water's meniscus climbs up the side. Water and glass like each other. Mercury hates glass, and so it minimizes contact. So this is liquid mercury. And so if the pressures are unequal, this is what's going to happen. Over here we have the weight of the air. So we call this the barometric pressure, or P sub B. And so that's the weight of the air. But what we'll do is we'll set a level here. Because clearly, the weight of the gas, in other words, the pressure of the gas is greater than the pressure of the air. So we see that the pressure of the gas is greater than the pressure of the barometer. Can you see that from this drawing? Yeah. And so, well, okay, but I want to know what the pressure of the gas is. Well, the pressure of the gas is going to be this. If I set this equal pressure line, then I have this. I have the weight of the atmosphere and the weight of this much mercury. And so the weight of this much liquid mercury, that's going to give us the pressure of the gas. Now, how much does that mercury weigh? Well, we don't actually weigh it. We're just going to measure the height of this in millimeters. If we measure the height of this in millimeters, then, and we know the barometric pressure in millimeters, then we just add them together. And so this is the equation I use. The pressure of the gas is equal to the pressure of the barometer plus the pressure of the liquid mercury. In the next scenario, let's say I have a different gas sample here. In this different gas sample, I look at the mercury. Here's one level of mercury, and the other level, let's say it's the same. So this is my liquid mercury here. And what can I say about this? Okay, over here I have the weight of the gas. Over here I have the weight of what? Barometer, or the barometric pressure. And when I look at it, well, they're at the same level, which means it's balanced, which means that the weight of the gas is the same as the weight of the barometer. The last scenario is if I'm looking at my gas and I have it connected to this U-tube here. Sometimes the gas pressure isn't as high. So. In this case, if I look at the weight of the barometric pressure and compare that with the weight of the gas is less. And so here the pressure of the gas is less, weighs less than the atmosphere because of the tilting of the balance. But what I do is I'll just draw this imaginary line across here and then set the two weights equal. They're going to be equal at the same level. And so what I'll do is I'll do the weight of the gas plus the weight of the mercury here. The weight of the mercury will just be how high this column mercury is. And so in other words, I get the pressure of the gas plus the pressure of the mercury is equal to the pressure of the barometer. In other words, the pressure of the gas is equal to the pressure of the barometer minus the pressure of the mercury. So that's the equation here that we have. So it depends on the scenario. But I don't like to memorize the equation for the scenario. And so do you memorize, use this equation for this one, use this equation for this one, but then when you have the middle one, which one do you use? I guess either one's okay. What I'd rather do is I just memorize this and then be able to figure out which equation to use based on rather than memorizing the equation here. And so the approach is a little bit different than the book. So let's look at an example of this.
Like P-bar, does it mean the atmospheric pressure?
Yeah, P bar and P atmosphere is the same. P bar is equal to P atmosphere. Same thing. It's just the pressure from the barometer. Barometer to measure atmospheric pressure. Let's see, I thought I had an example here, sorry. I don't have an example. Yeah. All right, let's try this. The pressure inside a steam boiler is 1,427 psi. Express this pressure in atmospheres. Why don't you try that? So let me know when somebody has the answer. Oops. 97.07. Yeah, that's to 4 sig figs. 97.07 is correct. Is that what other people got?
Yes.
97.07. That comes from, this is just a single conversion back. 14, you cancel out the PSI, get atmosphere, 14.70. And so we have 4 sig figs, 4 sig figs, 4 sig figs. So we're good. I'd like to see it. It's 97.074. I'd like to see that 4, and then I'd like you to drop the 4. Number makes sense. Should be close to 100 atmosphere. Okay, the pressure in an automobile tire is 29 psi on a day. The weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? So this problem has multiple parts to it. One part is how we define empty space. What is empty space? A vacuum. So when your helium balloon tank goes empty, is it really empty? No, it's not. You know, your helium balloon tank, when it goes empty, still has 15 psi of helium in there. It's just if it has 15 psi helium inside and there's 15 psi of air outside, the helium doesn't move. It'll diffuse out and things will get mixed, but it doesn't, come out of the tank with any force, with any pressure. And so when things are empty, they really aren't empty. They're still. And so when you're measuring your car tire pressure and it's reading 0 psi, did you just create a perfect vacuum in your tire? No, it's still filled with air, but now the air is at 15 psi. And so you go, well, that's wrong. It's not really 0 psi. And so we have 2 reference points. There are 2 0 points. And so this goes back to this slide back here. There's something called gauge pressure. Gauge pressure is the pressure above atmospheric pressure. And the reference point here is 0. 0 pressure means 15 psi, normal. And then we have absolute pressure. And so when somebody says, oh, today's barometric pressure is 29 inches, are they talking about gauge pressure or are they talking about absolute pressure? Absolute pressure. But if you say, hey, my car is inflated to 15 psi, you're talking about gauge pressure because of the reference point. Absolute pressure is reference to perfect vacuum. There's nothing there. Zero is zero. There's nothing there. However, gauge pressure is not. Gauge pressure is reference to an empty tank or an empty cylinder. And so let's say we're looking at a helium tank. And so it's gauge pressure is reference to atmospheric pressure. And so whatever atmospheric pressure is, that's going to be your zero on the gauge. So this is 0 psi. But to keep track of it, we call it psi-G rather than psi. And the other one is we would call it psi-A. So if we're at 0 psi-G, we're actually at 14.70 psi-A. In other words, that is if P atmosphere is equal to 14.70 psi. Because if the air pressure is at 14.70 and the gauge is reading 0, that means we still have 14.70 psi of helium inside the tank, helium gas. How do I get rid of that helium? By the way, you're never supposed to do this. You're never supposed to let the gauge go to 0. If you let the gauge go to 0, then they charge you an extra fee. This is when you reuse the tanks. You know those big tanks that you reuse? If you have a big tank of helium that you want refilled, you know, oh, my tank is empty, I need it refilled. If you actually return it empty, they're going to bill you. Why? Because if you return it empty to 0, they don't know if air leaked in. As long as there's still pressure in here, the helium is going to leak out. But if this goes to 0 and you left the valve open, then air can diffuse in and helium can diffuse out. And it contaminates the cylinder. If it contaminates the cylinder, they charge you extra because now they have to hook this up to a vacuum. And do you know what they do? They hook it up to a vacuum and then suck out the gas down here. They suck out the gas and then they have to backfill it. But is there such thing as a perfect vacuum? And so what they have to do is they have to repeat this. They vacuum, backfill it with helium. Vacuum, backfill it with helium. Each time they do that, they get purer and purer helium, and they get less and less air. And so they have to repeat this depending on how good their vacuum is. Now, if they had a perfect vacuum, they could do it in one shot. If they had a perfect vacuum, then it would go all the way, the gauge would go all the way to what? The gauge would go all the way to minus 14.70 psi G. And so we'd have minus 14.7 pounds of vacuum. Does that make sense? Because then they sucked out all the gas, and they only have to do it once. But normally they don't. They get high vacuum, and so they get maybe 10, minus 10. And minus 10 means there's still residual air. And so they're just kind of washing it out, rinsing it out, multiple rinses. Sometimes they'll do laundry and do multiple rinses. And the same thing, they have to do multiple rinses with helium to get rid of that air. Very expensive. So we never,
So assuming you were to just open the tank up, leave it there, because helium has a lower density than air, could you potentially just get rid of all of helium by leaving it open?
Yeah.
Okay.
Yeah, you get rid of, not all, because in air there's naturally helium.
Yeah.
And so there'll be a little bit of helium in there, but
it'll be a shift because
yeah,
it has a
it'll
higher
be a
density.
shift.
I mean,
Right.
lower density.
yeah, it has a lower density, but it's going to come out slowly
Yeah.
with diffusion. And the air will sink in here to the bottom, push out the helium. What was I going to say? But helium and air mix, so it's a little bit more complicated. Now, this is what we call a vacuum. If it's reading minus 14.70 psi-G, what is the psi-A reading? It would be 0 psi-A. That means if there's no gas in here, there's going to be no pressure, no collisions. Right? And then when we fill this, we'd like to fill it with a lot of helium. Let's say we get like 2,000. If this is reading 2,000 psi-G, what is its psi-A?
1,985.3.
That's not it. Try the other way. The other way. It's going to be 2014.7 PSIA. We have to add that 14.7 because of the 0 point. You know. And so, in other words, if we exchange the gauge, let's just change the gauge. Now I'm going to change the gauge to a P. This is a PSIG gauge. Now, if I use a PSIA gauge, it's marked down here. It's PSIA. Then the 0 means what? Can we have negative pressures on a PSI? No, the 0 PSIA means that there's nothing in there. But 0 PSIA would mean minus 14.7, 0 PSIG. And then if we just go to 14, let's say we go to 14.7, 0 PSIA, then the PSIG would be 0 PSIG. And then if we're at 2014.70 PSIA, what is the PSIG? 2000 PSIG. And so we look at the gauge. You know, the gauge here would be marked PSIG. The gauge there would be marked PSIA. There, you can buy either type of gauge. So the pressure in an automobile tire is 29 psi. Is that PSIA or PSIG? That's PSIG. The weather report states that the barometric pressure is 30.09 inches. How would you report? And so the first thing we got to do is figure out what PSIA is in any unit. Okay, so why don't you try to figure out what PSIA is, and then we'll convert it to kilopascals. Kilopascals is what some, like, if you look at some bike tires are marked kilopascals, you know, inflate to this many kilopascals. Why? I think they come from Europe or something. You ever pay attention to that? Do they have pumps with, do they have pumps with kilopascals? But I don't normally pay attention to that. Kilopascals is an odd unit. This problem is a combination of dimensional analysis and algebra. There are multiple ways you can do this particular problem. Did you get? What did you get?
I got 301.8 kilopascals.
301.8 kilopascal. You sound correct. They got 300, but they rounded it.
Yeah, I kept the whole 60s until I was all done.
Oh, that's good. There are a whole bunch of ways you could do this. You know, can you add? Basically, it's this. Do you know what it is? If we're reading PSIG, then PSIA is PSIG plus the barometric pressure because of the way the gauge works. The gauge is going to set 0 whatever atmospheric pressure is that day. So I just take this one. But if the atmospheric pressure is different, then the gauge is going to read 0 for whatever the day is. And so on this particular day, the barometric pressure is 30.09. Here. And so what we have to do is we have to add that to this, right? Because we're off by that much. So 0 point, it's like 32. We have to add the 32 to the temperature. And so either we could convert this PSI to inches, or we convert inches into PSI, or we convert PSI into kilopascals and inches into kilopascals. Which way do you want to go? Well, they did that. They converted PSI into kilopascals and then inches into kilopascals and then added the two. So let's just take a look at that. And so how do you convert inches into kilopascals? You need to know the conversion factor. Well, I know that 1 atmosphere is equal to 101,325 Pascal. That would be given. That's exact. And so to change it to kilopascals, we move the decimal 3 over. And then they're 14.7 psi per atmosphere. So we'll go from psi to atmospheres, and then atmospheres to kilopascals. We'll get the gauge pressure there. And then for the inches, we could use the conversion that we had up earlier for the inches. .92 inches to 1 atmosphere. So we'll go from inches to atmospheres and atmospheres to kilopascals. And so that would be the two-dimensional analysis problems we'll do separately. So here are the conversion factors there. The first dimensional analysis is PSI to kilopascals. Here they combine. I don't like combining conversion. I really dislike this. I dislike this because, you see things by sight, and you want to see the same things over and over by sight. That way you know what to expect, right? If you do this combination stuff, you know what I mean by combination? If you do this combination stuff, that's a weird conversion factor right there. And so I really dislike, this is something the book does a lot. And I have no idea why they do it, because we do dimensional analysis in little steps, right? And so this is what the book is doing here. They're going 29 psi. And I would do it like this. I would say, okay, there's 14.70 psi per atmosphere. And so that PSI's cancel, that leaves us with atmosphere. And then I would do this. I would say that there are 101,325 pascals per atmosphere. The reason is I don't want to memorize too many conversion factors. I just want to have a set of core conversion factors that I can string together. And so if I'm going to measure a whole bunch, I don't have enough room in my memory for that. And so the atmospheres cancel, and then I would just do this. I'd say that there are 1,000 pascals per kilopascal. And then do that. But what your book wants to do is they want to combine these into one. And if they combine that into one, then they're going to get 101.325 kilopascals per psi. Which is per 14.70 psi. But when I look at by sight, this is correct, this is correct, this is correct. Do I know that when I look at by sight, it doesn't automatically register. Okay, then they do the inches, and they do the same thing. For me, I would have done the inches like this. I'm going to convert the 30.09 inches into kilopascals. Actually, I'll do this after. We'll take a break now. We went too long. Take a break, and then we'll start.